last day we were drawing surfaces and curves in space, and recall the reason was that we want to study multivariable calculus. And in order to visualize the ideas, right, we draw these surfaces, they turn out to be very useful. And we took a number of them last day. What I'd like to consider today are two special classes of surfaces. First one are called cylinders. Now, you have in your mind what a cylinder is. And in fact, we had a couple of them last day. That x squared plus y squared equal to 1 is a cylinder, right? You draw that curve in the xy plane, and then you pull it in the z direction, it produces an infinite cylinder. Cylinders are more general than that. Some of the surfaces that we'll look at, you probably wouldn't have thought of as cylinders, but they are according to definition. What you do is you start with any curve in any plane whatsoever, but it's got to be a planar curve. I'm going to draw it in the xy plane, say that curve C. It doesn't have to be closed. I've made it closed, but it doesn't have to be. Right? So there's a curve in the xy plane. Then you take a line, any line you want in space, right? Call that L. And then what you do is, through every point on this curve, you draw a line parallel to that one. See, from this point you'd have that, on and on they go, going in both directions. That's called a cylinder, right? So through every point on C, draw a line parallel to L. The resulting surface is called a cylinder. So if we took this one, example 1, we took that curve in the xy plane, curve C. If I write this, would you like that? If I write that C is defined by x squared plus y squared equal 1, you'd have to say, hey, no, that's not a curve, that's a cylinder. If you put z equals 0 along with this, then you get the circle x squared plus y squared equal 1 in the xy plane. And what is L? What would you choose as L in order to produce this cylinder that we want, which is vertical? And the answer, choose L to be the z-axis. That will generate then the cylinder of radius 1 around the z-axis. So there's a cylinder, and there's its official definition. But let me write the following on the board. And ask you, is this a cylinder? 2x plus y is equal to 4. And your immediate reaction is saying, no, that's a plane, it's linear, therefore it's a plane. Okay? In fact, is it not? If I go draw this line in the xy plane, it's got an x-intercept of 2 and a y of 4. And I draw that line, and then I pull it in the z direction. Is that the plane described by this equation? And the answer is yes. Is it a cylinder? Yes. I can say my C is this line, and my L is the z-axis. So this is not only a plane, but it's also a cylinder. Personally, I'd rather think of it as a plane rather than a cylinder, but it does satisfy my criteria to be a plane. Do you notice anything about these two situations in particular? Well, I think all you notice is here, no such. Here, no z's. Both of those could be regarded by drawing this curve in the xy plane, curve in the xy plane, and then pull this out. Right? Suppose example 3, I gave it z is equal to x squared. Right? Is that a cylinder? Could you regard that as being some curve, somewhere, some line, somewhere, that if you do this, you'll get that thing? The answer is yes. Notice that there's no y here. What does that mean? It means if you were to intersect this with the xz plane, you would get the parabola z equal x squared. The fact that there's no y there says that y can be anything, right? So take that and pull it in the y direction, right? And what do you get? A cylinder. What I actually call a parabolic cylinder. Its cross-section is a parabola, right? In fact, could we take this further and say, if you have a surface and one of the variables is going to be missing from that equation of that surface, then you're automatically going to produce a cylinder. And the answer is yes. All right, if say that y is missing, draw whatever is in the xz plane, pull it in the y direction. If the z is missing, draw whatever you see in the xy plane, pull it in the z direction. So once variable is missing, when there's a variable missing, then you're going to get a cylinder. If one variable is missing in the equation of a surface, the surface will be a cylinder. In general, there's always exceptions, but this is what I'm going to expect in general. So that's a nice way to recognize cylinders. In fact, I always look, if you give me the equation of a surface, and I look at it and I say, is anybody missing? Because I automatically know that it's a cylinder, and I know how to draw that curve in the plane of the missing the other two variables, and then pull it in the direction of the missing variable. That isn't to say all cylinders. Remember this from last day? We didn't like it from last day. We had the surface y was equal to z plus x squared. That one probably was the most difficult one that we had to draw last day. I'll try and reflect you for what it looked like. We had this line y equal to z, and then through this line y equal to z, we do parabolas that were parallel to the xy plane. Remember that surface? Not the easiest one to draw, right? So from this line y equals z, you draw these parabolas, right? Is that a cylinder? The answer is yes. If you take the one parabola down here in the xy plane, and then you draw through every point on this parabola a line parallel to this y equals z line, you produce this surface. So that was a cylinder too, right? So we've seen lots of cylinders before. We just didn't call them cylinders. We hadn't invented that word yet. There's another whole bunch of surfaces that constantly seem to keep coming up. They're called quadric surfaces. I often give students difficulty in drawing them, but they are a favorite, especially when it comes to drawing surfaces that surround volumes and finding the volume surrounded by those surfaces later on. So remember conic sections in the xy plane? Things called parabolas, circles, ellipses, hyperbolas. they all came from equations of this form. Equations of that form give rise to what are called conic sections. We never in first year had any term that looked like that. That one was simply not there, right? What that term does is takes an ellipse or a parabola or a parabola and rotates it around the origin. And we never looked at those. We could have, but we didn't have time, right? And the rest of them then describe that normal conic sections. Like if A and C are both equal, then that's going to describe a circle. If A and C are both positive, right, but not equal, then you're going to have yourself an ellipse. If A and C have opposite sides, you're going to have yourself a hyperbola. If one of these is missing, right, then you're going to have yourself a parabola. So you can see that all of those curves that you studied are special cases of this. We now want to talk about the following equation. We're going to move it up into 3 space and talk about the general quadratic equation in x and y and z. So we would have an ax squared, we would have a by squared, we would have a cz squared, we'd have a dxy, we would have an eyz, we would have an fxz, we would have an hx, we would have an iy, and we would have a j equal to 0. So that's the counterpart of this one when you got 3 variables instead of 2. We don't want to consider this in this great generality. That's just too much of an undertaking. We're only going to consider, really, primarily but not exclusively, like only a couple special cases. We're never going to have these and these and these, because they represent rotations that we just don't want to get involved in. Right? But we're going to look at the special cases of ax squared, by squared, cz squared is equal to j, and ax squared, by squared is equal to iz. We'll only look at surfaces that look like this, primarily, not exclusively, but primarily. So we've left out all these cross terms, right? And now we're looking at this. Now, it could be that for instance, in this one, this could be the x and this could be the z, right? So we don't have to have them exclusively in that order. But anything that has that form with x's and y's and z's interchanged is what we want to look at and discover what do these surfaces look like. So let's take some examples. In fact, there are 9 different ones. And you can see the textbook. All 9 are drawn in the textbook. I just want to consider a few of them to give you an idea what they look like. And anything that I don't do in class, you still will need to know about them. So let's do this one. Z is equal to 3y squared. Example 1 for quadric surfaces. Z is equal to 3y squared. Well, let's say, and that would be this one if you put the I equal to 1, you put the A equal to 0, and you put the B equal to 3. Then you'd have this one. So it is an example quadric surface. But you know what this one looks like. There's no axis, therefore it's automatically a cylinder. So you want to draw it. X, Y, Z. You would go to the YZ plane, draw this parabola, Z equals 3y squared, and then you would pull it in the x direction. You say, there it is. Parabolic cylinder, right? So this is a parabolic cylinder. Nothing new there. We've seen those before. Example 2. Z is equal to 4x squared plus 7y squared. Not a cylinder, agreed? Not a cylinder. But you should recognize this one Because we drew this before. What's that? That's a bowl. What do the 4 and the 7 do? Well, instead of getting a circular bowl, it turns out when you take cross sections with z equal to k, you cross section with z equal to k, and you've got 4x squared plus 7y squared, this curve in that plane, and that's an ellipse. So instead of having a circular bowl, what we would have would be an elliptic bowl. Right? So here it is, an elliptic bowl. So there are a lot of scales on there. You can't tell whether that cross-section is circle or ellipse. But scales on there, then I'd have to be careful. Right? This is not called elliptic bowl. Bowl is not a very mathematical word. It is called an elliptic, that's not a real, paraboloid. So this one's called an elliptic paraboloid. You see why the word parabola is kind of buried in there? Well, the answer is yes. If you were to take the YZ intersection, then what do you got? A parabola. If you take the XZ intersection, you've got a parabola. So we call this an elliptic paraboloid. Right? But again, that's really nothing new. We've seen those kinds before, and they're special of what we wanted to look at. Here's one that perhaps is most difficult for students to draw. Z is equal to x squared minus y squared. To draw this, let's go back to first principles. Let's go back and take some cross sections. Maybe by drawing some cross sections, we would be able to piece this surface together. If we cross-sect it with the YZ plane, you put x equal to 0. That gives you a parabola that opens down. So visualize that's in the YZ plane, right? Parabola opening down in that plane. Then if you cross-sect it with the XZ plane, you put y equal to 0, and you get a parabola that opens out. So there. So those are those two parabolas. What if you intersect it with the xy plane by putting z equal to 0? You put z equal to 0, what do you get? X squared minus y squared is equal to 0. That means x is equal to plus or minus y. Two straight lines, one this way, one that way. Oh, good God. I can't look at that and see parabola, parabola, two straight lines and say, I see the surface. If you can, you're better than I. So I'm going to try this again, but I'm going to take intersections that are perhaps more revealing than these ones. So let me try and show you a better one. I like Let me think here. All right. The z equal minus y squared. It was the one that came down here like that, okay? All right. Now let's cross-sect this with z is equal to k. Getting therefore, along with z is equal to x squared minus y squared. And then we're getting x squared minus y squared is equal to k. This curve in that plane. What's that the equation of? That's the equation of hyperbola. All right? So you go up here to the plane x equal, or z equal to k, and then you draw this hyperbola, right? Then you draw that hyperbola. All right? This one perhaps isn't the one that's most revealing. Let me draw that z equal x squared. That's one, that's that one, that's that one. Okay. So if saying that, so there's one cross section. Now if we move up to this plane up here like that, and we intersect it, we're going to get a hyperbola. What about this hyperbola? So visualize that you're up here somewhere, and you draw this hyperbola in that plane. What does it do? Is it going to be here and here? Are those 2 points, all right, going to be on it? Right? Now remember, this is a plane that's k high. Okay, k high. And if you put y equal to 0 in here, what do you get? Oh, plus or minus k. So that's these guys right here, right? Okay. So it intersects there, and it intersects there, there's hyperbola. And which direction does it go? It doesn't have any y, okay? It doesn't have any y-intercepts. Which way does it go? Does it go like this? Good grief, I'm having trouble with this one as well. Okay, which way? I just go like that. All right, is that hyperbola? Now try and visualize that when you come down to here, then you're getting the same hyperbola, right? So can you visualize then, you've got this parabola here, and then you've got these hyperbolas, which all have the same shape, but just shifted up, okay? Coming from it. Can you visualize that surface? I don't say it's the easiest thing to do. Perhaps here's a good description, okay? Remember we had this curve down here. Think of it as a saddle, right? Now you got the saddle, right? Right? So you sit on it, right? And your legs come down here, right? And this is the front of the horse, and this is the front, saddle going front, and this is towards the rear of the horse, okay? So you're sitting here like this, and it's going down there, and then it's coming up, right? Up at the back, right? So you've got that thing there. Not the easiest thing to draw. What do we call it? It's got hyperbolas in it, hyperbolic, and it's got parabolas in it, a hyperbolic paraboloid. But not the easiest one to draw, but that's how I kind of envisioned it, as looking like a saddle, right? Next one. X squared plus y squared minus z squared is equal to 1. When I look at many of these quadric surfaces, I kind of key on to that thing there. But that makes me think about circles. If you put a 3 here, I still would key on that thing, oh, ellipses, all right? What does that suggest I do? I'm thinking circles there. It's only a circle if the z weren't here. So I think I'm going to put z equal a constant and take cross sections, producing therefore circles and trying to piece these circles together. But I'm clued in. So let's put z is equal to k here. So I'll have x squared plus y squared minus k squared is equal to 1. We take it over to the other side. We can write plus k squared. So the intersection of this surface with this plane is this curve. It is this curve here inside that plane. All right. So let's see if we can put all of that together then and visualize the surface. So let's start taking some values of k. Is this one? K equal to 0. If you put k equal to 0, you get x squared plus y squared equal to 1. It says this surface, whatever it looks like, intersects the xy plane in a circle of radius 1. If you take k bigger than 0, right, which means you're moving the cross-section up, whereas you put k equal to 2, then this would be 5. So you've gone up to plane too high, this is 5, it's now a circle of radius 5. The higher you go, always a circle, but the rays getting bigger and bigger and bigger. Hey, I think it looks like this. And the same thing down here. I think that's what it looks like. What do you think I should do to kind of put some more verification into here? How come I didn't draw these things straight? Maybe they should be straight. How would I check? I'll take another cross section. Let's put x equal to 0 along with that equation. Then we're going to have y squared minus z squared is equal to 1. So this curve is the curve intersection this surface with the yz plane, and that's a hyperbola. So this is hyperbola. That is hyperbola. You take any vertical cross section, you're going to get yourself hyperbola. I think we got the picture correct. What do we call it? We call it an elliptic hyperboloid of one sheet. Having said that, you probably guessed there's going to be others that are not one sheet. And yeah, that's coming in a minute. Okay? You can see the word elliptic. If I were to put a 3 here, then these wouldn't be circles, they would be, you might want to call this a circular hyperboloid of one sheet. But elliptic covers them all. For any number you put here and any number you put here will be positive, then you get an ellipse. So there's that one. Next one. Example, whatever. Z squared minus 4x squared minus y squared is equal to 1. What about that? Well, remember when I talked about this one, I kind of keyed into the x squared plus y squared. I would do the same thing here. I would key into not that, because if that's not there, that's hyperbolas. I hate hyperbolas. Right, but that's not there, then hey, I'm starting to kind of think about ellipses. So I'm going to key into writing 4x squared plus y squared is equal to z squared minus 1. And then I'm going to do the same thing I did here. I'm going to cross-sect it with horizontal planes, producing, therefore, I think, ellipses. So let's do that. So let's intersect with z equal to k. If we do that, we get 4x squared, and a y squared is equal to k squared minus 1. So the intersection of this surface, whatever it looks like, in the z equal k plane, is this curve in that plane. And now I'll start diagonalizing k in. But you'll notice if you try k equal to 0, you don't get anything. Back there we did, but here you don't. In fact, you can't put into here any value of k between 0 or between minus 1 and plus 1, because it doesn't make sense. So you have to choose k to be greater than or equal to 1, or k to be less than or equal to minus 1. The only way you're going to get anything. If we put k equal to 1, then this becomes 0, and what does this tell you? That's a 0 saying 0, 0. So if you go to the k equal 1 plane, and you cut through the surface, you get 1 and only 1 point right there. So this, and that's 1. Okay? 0, 0. Right? So z is equal to k is equal to 1, so z is equal to 1, and you get x and y both 0, you get that. Now, if you make k larger than 1, okay, this will be positive, and therefore that will be an ellipse. And the bigger the k, the bigger the ellipse. So as we go up from there, we get ellipses that are getting bigger and bigger and bigger. Would you surmise, therefore, would you see this is what it's going to look like up there? And it doesn't matter whether the case positive or negative, you're going to get exactly the same thing down here. -1. This one they call, much like this one, elliptic. You see elliptic, hyperboloid, because there are hyperbolas in here, we just haven't seen them, of 2 sheets. So this is elliptic, hyperboloid, of 2 sheets. So there are some of the 9 different kinds of quadric surfaces. Drawn here, I think the ones that cause most difficulty for students in general. What you have to do, go practice. One other thing in this section, and something we need not for a while, but when it comes to calculating volumes bounded by surfaces, what we will have to do is take curves in space and project them onto either the xy plane, or the xz plane, or the yz plane. So projecting space curves onto coordinate planes. I want to do 2 examples to illustrate it. Suppose I give you the following surface. X squared plus y squared equal 1, which is now common knowledge to us, and x plus z is equal to 2. We have here a cylinder wrapping around the z-axis, radius 1. We have here a plane. All right? So let's draw this, visualize the curve, and then ask what I want. So you've got the cylinder of radius 1. And then we have this plane. There's no y's there, so we could draw this as a line in the xz plane and then pull it in the y direction. So we've got this was a 1 and a 1. So it's cutting at 2, and it's cutting at 2. So visualize, whoops, didn't do that very well. Join those 2 points to make a line, and then pull it in the y direction to make a plane. Can you visualize that? And this curve then is the curve of intersection of the plane and the cylinder. So let's take that one out for a second. Right? So can you visualize that plane slicing through the surface to produce this curve of intersection? Visualize that. Here it comes, up here and slicing through. There's got to be something like that. That's a plane slicing through the cylinder, or that curve of intersection. Can you visualize that? You can draw a better picture than that. Okay? All right. So what we now want to do is say, I want to take this curve and I want to project it down into the xy plane, which means visualize that you got a light way up there on the z-axis, you shine it on the curve, and you look for the shadow in the xy plane. That's what I kind of mean by the projection. Just visualize a light up there shining down on the curve, and the shadow down in the xy plane is a projection. Well, I don't think it takes too much imagination to say that because that curve lies on that cylinder, then that projection is going to be this curve right here. That's going to be the shadow right there. So projection in xy plane is curve z equal to 0 along with x squared plus y squared is equal to 1. There's the projection in the xy plane. That's relatively easy to see. All right? Now let's go for the projection in the yz plane. Projection in the yz plane. Right? Well, if it's going to be in the yz plane, it's going to be a curve. So visualize then you're taking this light, right, way out here in the positive x-axis, shining it back up there, and visualizing what does it project onto in the yz plane? What is the shadow in the yz plane? Well, if it's going to be in the yz plane, then there can't be any heads. So what you do is you take these two equations and you eliminate the, it's going to be in a yz plane, there can't be any x's. So you take these two equations and you eliminate the x, which I would do is to say x is equal to 2 minus z, and I would put that into there. So we eliminate x. And we would get, therefore, that y squared plus the x, which is 2 minus z squared, is equal to 1. Or if you like, y squared plus z minus 2 squared is equal to 1. And this is in the yz plane. What's that? That's a circle. Right? In the yz plane, that's a circle. Right? What's its center? 0 and 2. How high was that? What was that? That was 2. It's saying it's right there. That this is a circulus plane of radius 2. Does that look reasonable to you? That you look in there and you say, do I see a circle? All right, centered at 2 and the radius is 1. The answer is yes, that looks good. All right. 1, 2 down, 1 to go. Projection in the xz plane. Well, if we follow this, it would say eliminate the y. So you take these two equations and you kill y. Answer, well, I'm doing anything there is. This guy got no y's in it, so it's x plus z equal to 2. So let's say you take and you look this way in there, and you say, hey, curve. What are you projecting back there? Is it reasonable to you that it would project onto this line, which I took off, and put it back on again, that the projection will be that line? That circle on the cylinder is going to project onto that line. And I can see that. But there's a slight difficulty. That line goes on forever, and the projection doesn't. Right? The projection is only part of the line. The question is, what part? How much of the line do we want? Well, remember, it's in the xz plane. Hey, it's going to go from here back to there. How much is x here? Answer, 1. What's x back there? Minus 1. So we would only go minus 1, less than or equal to x, less than or equal to 1. Only that part of the line is the projection of that circle in the xz plane. So the obvious projection is the downward one. Okay? The other two are not so obvious. One last example of this idea of projecting. So let me take a new example. z is equal to x squared plus y squared, and 2x plus z is equal to 1. You know what this is? That's a bowl. Or if you like, a circular paraboloid bowl that opens up. 2x plus z, plane, draw that in the xz plane, pull in the y direction. Z equal to 1, x equal to half, so that's 1, that's a half, join those up, pull it in the y direction to make a plane. Visualize that plane slicing through the surface, all right? Can you visualize that plane slicing through the surface to produce the curve of intersection? Would you say, with not the best artwork in the world, something that looks like this? That's a plane slicing through that parabola bowl to produce something that looks like that. So we can accept that picture, you can visualize it. Let's go find projections in the various planes. XY plane. With the XY plane, what do? We eliminate Z. So if we eliminate Z, how we have solved this for Z, 1 minus 2x, and put it there. 1 minus 2x is equal to x squared plus y squared. What's that? That's a circle. I wanted to see it, we write x squared plus 2x, y squared equal to 1, x plus 1 squared, y squared is equal to 2. Right? So it's a circle centered back here at minus 1 and a radius root 2. So visualize a circle here. Does that look reasonable to you? That if I project that curve down, I would see a circle back here at minus 1 center. The radius root of root 2, which is taken out to about here. That looks good. All right? So how's that? There's the projection of that curve. Right. A question may come out later in my new analyticals. Find the volume bounded by those surfaces. Right? So it would be on top of the bowl and under the plane. You can visualize that. I would need this equation in order to solve that problem. I would have to project this curve into the xy plane. I could try other projections, but this would be probably the best one. Right? Okay. So let's see now. That's one down, 2 to go. Projection in, let's go for the xz plane. XZ plane. That means we would now eliminate y. Eliminate, oh, I don't have to do too much. There it is. 2x plus z. Does that look reasonable to you? When you take this curve and you project it back into the xz plane, it's going to be precisely lying on this line in the xz plane because that's where this curve came from, is slicing through. Yes! But it's not the whole line again. The question is how much of it? Well, I guess it would be from here back to somewhere over here would be only that part of this line. We need to find those coordinates of those points. We need the x values of those 2 points. X values. Oh! The y coordinates of those points are 0. So if we put y equal to 0, for y equal to 0, then we're going to have have z is equal to x squared, and we're going to have 2x plus z is equal to 1. Right? Okay. So all we have to do is solve these two. So if I solve those two equations, I get the x and z coordinate of this point and that point. And I'm really only interested in the x one. I could do the z's, but I'll do the x's. Okay? So if we want the x's, why don't we put that in here? For that z, put x squared. So we have x squared plus 2x equals 1. X squared, 2x minus 1 equals 0. Quadratic. X is equal minus b plus or minus square root b squared minus 4ac all over 2a minus 1 plus or minus 8 to root 2. There they are. There's the x coordinate of that point and that point. So we'll say this, provided we have minus 1 minus root 2 less than or equal to x less than or equal to minus 1 plus root 2. So it's only that part of the straight line is this projection. 2 down, 1 to go. Projection in the y-z plane. That means this time we eliminate x. Eliminate the x. Eliminate the x. How about we solve this for x and put it into there? So z would be equal to, eliminate this, solve that for x, 1 minus z over 2 squared plus y squared. Solve this for x, 1 minus z over 2, put it in here, squared. There's the curve intersection in the yz plane. So visualizing, taking this thing and projecting it onto the yz plane. What's that? Why don't we square this up? Z is equal to 1 over 4, 1 minus 2z plus z squared plus y squared. Let's multiply by 4. 4z, 1 minus 2z, z squared, 4y squared. Want to bring the z's together? Z squared minus 6z plus 1. Let's put the 1 over. Plus 4y squared is equal to minus 1. So I put 1 on the other side here, and I put everything else on the other side. Complete the square. Z minus 3 squared, 4y squared, equal to 10. There's the 9. What do you got? An ellipse. Would you agree that it's not unreasonable that the yz plane, this thing projects onto an ellipse? What? So there then are the 3 projections of that curve of intersection of those 2 surfaces. What I would like for you to do, if you can, and would be willing to, is next day I'm going to talk about material briefly to do with vectors. You had vectors in 1210. You dealt with them, you talked about dot products, you talked about scalar products. Dot products, scalar, same thing, cross products. You talked about equations, lines, and planes. I'm going to review some of that material quickly, but if you reviewed it, then my review would be that much more comprehensive.